Those who frequently traverse the landscape of space and time understand that, theoretically, wormholes represent a bridge through the continuum, a way to return to any desired moment in history. Today, we examine a thought experiment involving a wormhole stretching from lunar orbit to a desolate stretch of space near Neptune, where a welcoming party has already gathered. Human civilization has expended immense effort and resources to capture a wormhole from the depths of the quantum foam, a phenomenon long predicted by general relativity that has finally manifested in reality. With this technology, the dream of interstellar travel seems within reach. Following final calibrations, a spacecraft and its courageous crew enter the throat of the wormhole, crossing the spherical boundary of the entrance with ease. Observers watch as the ship recedes and shrinks, appearing to glide effortlessly toward its destination. Over 4 billion kilometers away, the reception team sees the vessel approaching. As it gradually enlarges, previous unmanned probes crossed this distance in approximately 30 minutes, and this manned mission appears to be on a similar trajectory. However, whispers of concern soon ripple through the crowd. The ship seems to decelerate until it stops entirely, as if frozen in place. 30 minutes pass, then days, weeks, and eventually months. High-precision telescopes at both ends of the wormhole confirm that the ship is still moving, but at a speed that is almost imperceptible. Debates erupt over a potential rescue or whether to shut down the wormhole generator, but every option seems destined for tragedy. The exotic forces required to maintain the stability of the wormhole are so delicate that any imbalance would instantly tear the ship and its crew apart. It is a long story, one perhaps better suited for the realm of dreams, but before we proceed, please remember to like and share this journey. 5 centuries later, the wreckage of the ship finally emerges from the far end of the wormhole. It remains intact but non-functional, a hollow shell of its former self. After ages of bombardment by the harsh environment within the tunnel, the crew has long since perished, their remains still strapped to the command consoles. The wormhole is eventually deactivated, revealing a stark truth: the calculations were wrong. The predictions of general relativity alone were insufficient. The scientists believed they had mastered the complex intersections of gravity and quantum mechanics, having accounted for every known interaction, yet something fundamental went awry. Humankind gazes at the distant stars, feeling a profound and unprecedented sense of loneliness. Wormholes are inherently complex, while they appear in the equations of general relativity, a theory nearly a century old for those lost on the way to Neptune. Relativity was merely a machine. We must observe how these theories function in different contexts, but that does not guarantee the universe permits such scenarios to exist in reality. What conditions are required to build a functional wormhole? What mechanisms allow them to persist, and which forces strictly forbid them? Can they truly carry us to the shores of the stars we dream of, or do they merely propel us toward a premature end? Critics once called it chaotic and absurd, yet for Edgar Allan Poe, it was his crowning achievement. In 1848, a year before his mysterious death, Poe penned a work he considered the ultimate goal of his literary career. Titled Eureka, this sprawling discourse is far less famous than his poetry today, yet hidden within its dense prose are insights that were remarkably ahead of their time. Discussing interstellar space, Poe wrote that space and time are one and the same, a singular entity with no inherent distinction. Nearly a century later, Albert Einstein, unaware of the poet's intuition, echoed these thoughts during his miracle year of 1905. Einstein's special relativity demonstrated that measurements of length and time depend entirely on the observer. However, it was his former teacher, Hermann Minkowski, who provided the geometric interpretation, describing the universe as a four-dimensional manifold where space and time are different facets of a unified reality. Einstein embraced this vision, leading to the monumental leap of general relativity in 1915. In this framework, space-time is not a static stage but a dynamic fabric that reacts to matter and energy. As physicist John Wheeler later summarized, matter tells space how to curve, and space tells matter how to move. This interaction happens all around us. Gravitational waves from distant cosmic catastrophes stretch and compress the space we occupy, though on a scale so small it is almost undetectable. General relativity acts as a theoretical machine. You input the distribution of matter, and it outputs how that matter evolves under its own gravity. Yet, it does not dictate whether such matter distributions actually exist in nature. Much like Newton's laws, the equations provide the mechanics of movement but do not account for the reality of the structures themselves. The scientific community recognized the validity of Einstein's work, yet many found the 10 interconnected, nonlinear equations too difficult to handle. Nevertheless, breakthroughs occurred. Shortly after the theory was published, Karl Schwarzschild found a solution while in the trenches of the Great War. His results described the gravity around a mass like our Sun, but they also hinted at a singularity, a point of infinite density where a star collapses beyond a critical limit, surrounded by a one-way boundary known as the event horizon. While Einstein himself doubted that such objects could truly exist in nature, Robert Oppenheimer and his students calculated that a sufficiently massive star would inevitably collapse into such a state. Despite their work being interrupted by the Second World War, evidence eventually confirmed that black holes are real. But was this the extent of the theory's predictions? In the Soviet Union, Igor Novikov realized that the equations of relativity do not care about the direction of time. If a black hole eternally consumes matter, its time-reversed counterpart, a white hole, must exist to eternally eject it. While white holes remain controversial, Roger Penrose and John Wheeler realized these solutions could represent a tunnel to another universe. Wheeler eventually coined the term wormhole for these bridges, though scientists still struggle to determine if they are prophetic glimpses of nature or merely mathematical fantasies. Among the brilliant minds working in Einstein's shadow was Nathan Rosen, who joined Einstein at Princeton in the 1930s. Together, they sought a way to eliminate singularities by describing particles as bridges in the fabric of space. This led to the Einstein-Rosen Bridge, a concept where a path through a black hole does not end in destruction but emerges in another region of the universe. Decades later, John Wheeler revitalized this idea, imagining these bridges as shortcuts through the stars. Yet, even as he championed the concept, Wheeler recognized the fatal flaws, the laws of physics beyond gravity and the inherent instability of such tunnels. While black holes have been proven to exist, the white holes necessary to complete the wormhole connection remain an elusive and perhaps impossible dream of the cosmos. White holes are essentially the temporal reflections of black holes. They exist in theory only because general relativity is indifferent to the direction of time. However, we are not indifferent. And neither are the other laws of physics, such as thermodynamics. The second law of thermodynamics forbids a decrease in entropy. While a star can collapse into a black hole, an event where entropy increases, the reverse process of matter spontaneously expanding into a white hole would require entropy to decrease, which is strictly prohibited. Consequently, there is no known mechanism in the universe that allows a white hole to form. Even if they had emerged during the early moments of the Big Bang through some exotic process, they could not have survived. Encountering one would be a surreal experience. You would be drawn in by its gravity but find yourself eternally barred from crossing its anti-event horizon. You would be trapped at the edge where energy levels skyrocket until the system becomes unstable and inevitably explodes. Thus, white holes remain mathematical fantasies within Einstein's equations, unlike their real-world black hole counterparts. Yet, dreamers like John Wheeler and Igor Novikov were not satisfied with this conclusion, believing that a future, more refined theory of gravity might one day grant these objects a place in reality. In the search for accurate physics within popular culture, one often finds that franchises like Star Wars prioritize spectacle over science, with lasers slower than bullets and space stations that defy gravitational logic. Occasionally, however, creators strive to align with our actual understanding of the cosmos. A prime example is Christopher Nolan's Interstellar. Seeking a way for his astronauts to traverse vast distances without violating the universal speed limit of light, Nolan consulted the Nobel laureate Kip Thorne. Thorne explained that faster-than-light travel is impossible, proposing instead a stable, traversable wormhole. This concept was not entirely new to Thorne. In the 1980s, his friend Carl Sagan had made a similar request while writing the novel Contact. At that time, wormholes were proven to be extremely unstable, but Thorne and his colleagues set out to find a theoretical way to keep them open. In a landmark 1988 paper, they explored the use of wormholes for interstellar travel. They realized that the bridges envisioned by Einstein, Rosen, and Wheeler were non-functional because they collapsed too quickly. To make a wormhole traversable, two major hurdles had to be cleared. Thorne discovered a clever mathematical trick. Instead of calculating the curvature caused by a known distribution of matter, he worked backward, designing the desired space-time structure first and then asking what kind of energy would be required to sustain it. The answer provided by the relativity machine was exotic matter, specifically, matter with negative mass. This is not to be confused with antimatter, which still possesses positive mass. True negative mass would repel rather than attract. A shell of this exotic substance would exert outward pressure, propping the wormhole entrance open and preventing the tunnel from collapsing. However, negative mass has never been observed and would seemingly violate the conservation of momentum, a cornerstone of modern physics. If you kicked a ball of negative mass, it would fly toward you rather than away. Yet, because matter and energy are two sides of the same coin, scientists began to wonder if negative energy could serve the same purpose. This line of inquiry leads back to an unlikely source, a mock cowboy gunfight in post-war Copenhagen involving a young researcher named Hendrik Casimir. Inspired by the dynamics of reactive forces, Casimir calculated that two unchanged arced metal plates placed incredibly close together in a vacuum would spontaneously move toward each other. This occurs because the plates restrict the quantum fluctuations of the fields between them, creating a region where the energy density is lower than that of the surrounding vacuum. This phenomenon, known as the Casimir effect, represents a real-world manifestation of negative energy. If focused in sufficient quantities, it might theoretically stabilize a wormhole. Such a wormhole would be a spectacular sight. Its entrance would be a shimmering sphere, reflecting not the local environment, but the light from the stars on the other side. You could wave to a friend in the Andromeda galaxy or step through the portal to travel millions of light-years without feeling the slightest gravitational strain. Unfortunately, the transition from mathematical solution to physical reality is fraught with difficulty. Physicists use a set of rules called energy conditions to determine which solutions are physically permissible. While the Casimir effect violates the weak energy condition on a microscopic scale, it remains uncertain whether a macroscopically stable wormhole could ever be constructed. Beyond the engineering challenges, there is the deeper problem of time. Stephen Hawking once famously hosted a party for time travelers, sending out the invitations only after the event had ended. When no one showed up, he concluded that time travel likely does not exist. However, the equations of general relativity still permit it. If one could move one end of a stable wormhole at near light speeds, time would dilate for that end relative to the other. By traveling through such a bridge, one could theoretically arrive at a destination before even departing. This possibility introduces a host of paradoxes that lead many physicists to believe wormholes must be forbidden. If you could travel back in time and destroy the very machine that sent you there, the logic of the universe would collapse. Igor Novikov proposed a self-consistency principle, suggesting that the past cannot be changed. Any action taken by a time traveler would have already been a part of history. Conversely, Hawking proposed the chronology protection conjecture, suggesting that the laws of physics conspire to prevent closed time-like curves from ever forming. Perhaps wormholes are not tunnels to our own past, but bridges to parallel universes as described by the many worlds interpretation of quantum mechanics. In this view, every quantum event splits the universe, and a wormhole might simply be a path to a different branch of reality where Hawking's party was a resounding success. Even as recently as 2019, researchers at Harvard and the Institute for Advanced Study found new ways to construct wormholes in specific mathematical models that do not require exotic matter, yet these structures prove to be agonizingly slower than traveling through ordinary space. Today, the consensus is that while wormholes may remain prohibited in our specific universe, they serve as invaluable laboratories for the mind, pushing the boundaries of gravity and quantum theory. As Hawking once remarked, God not only plays dice, but sometimes throws them where they cannot be seen. We conclude our journey into the unknown here. May your dreams be filled with the wonders of the cosmos until we meet again.